In this video, we're taking a look at conservation laws, both gravitational potential energy and energy conservation, as well as angular momentum. Um, this is going to allow us to talk a little bit more about escape velocity and other things, black holes even, which is kind of fun. So we remember that the orbital motion, where we have gravitational potential energy, was something that we talked a lot about in terms of forces and acceleration. But the other piece that you can look at is the mechanical energy of the system. Well, it's obviously the kinetic plus the potential. But we already know that the potential energy is negative gmm over r, and the kinetic energy is 1/2 mv squared. And since it's a circular orbit, we know that the centripetal force equals the force of gravity. And we've already learned that the velocity or the orbital speed is the root gm over r. So we can put all that together. We end up with the total mechanical energy is 1/2 m times gm over r. But that's interesting because we end up with 1/2 gmm over r minus gmm over r. So we get negative 1/2 of gmm over r, which happens to be 1/2 of the gravitational potential energy. And this is actually a really special case. That the gravitational or the total mechanical energy for a circular orbiting system is going to be equal to 1/2 of the gravitational potential energy at that point. And this will be a negative value, and it should make sense. If it was in orbit, it hasn't achieved escape velocity, and if it achieved escape velocity, it would have a total mechanical energy of 0. So conceptually, if we look at the gravitational potential energy curve here, right, however much energy there is, the total should tell us where the orbit is, right? If the total mechanical energy is some distance, is some area, the kinetic energy is the difference between the gravitational potential energy and the total mechanical. As the orbit gets smaller, the little rays get smaller, we get more and more negative. And this is kind of why we call these gravity wells. The object is trapped in an energy well. And if you remember our potential energy curves, where we said the turning points were the places you couldn't go beyond, that was where the mechanical energy intersected the gravitational potential energy. So for any orbital system, right, which really is an ellipse, we can say that there are 3 conservation laws. Total mechanical energy is conserved, because only conservative forces do work. Just the gravitational potential energy is there, or gravitational force. The angular momentum is conserved because no external torques act, and the linear momentum of the system is conserved. That one may not be quite as obvious, but it's also true. There's no net external forces acting on the system, right? If you draw the system as that red dotted line around our planet and star. So objects orbit the center of mass, which stays at rest. And that's kind of the important piece. What else can we say? Well, we can also say that if you're only looking at the satellite or the planet or whatever it is here, then the linear momentum isn't conserved, right? Because there's an external force acting on the satellite. And that ends up being the differentiation. So let's look at Pluto. Pluto has an elliptical orbit, maybe not a planet, but looks something like this. The perihelion and aphelion, right, we're at our max and min velocities. And the eccentricity is about 0.25. The A, some major axis, is given. What is V max and V min? Well, the way to approach this would be to think of it as an elastic collision. Right, we have 2 equations that we can solve for 2 unknowns. We know the angular momentum is conserved, and we know that the mechanical energy is conserved. So conservation of angular momentum. Since they're point particles, we're going to do m times r times v, or in other words, r times the linear momentum at the 2 points. And we can find that VA is VP times this ratio rate of distances. So we need the other equation to figure out the rest. Conservation of mechanical energy is our second equation. We can plug all this in. We get some R values here, and we can combine everything together by canceling out that mass, simplifying a little bit, combining the 2 equations, plugging in what we knew before, and then doing a little bit more simplification. And we have numerical values for these, so we can plug them in. Solve for VP. It's a kind of messy equation, but we can actually find the velocity at perihelion and aphelion. Once we've done one of them, you can find the other because we have that simple relationship between them. And what you see, hopefully, is that the velocity at perihelion is much bigger than the velocity at aphelion. And how big of a difference depends on the ratio of the RP and the RA values, the distance from the sun at perihelion and aphelion. So this leads us to a question, right, with escape velocity. What can you not escape from? That's a black hole. And it's called a black hole because even light can't escape. You probably know all about that. Anything that passes within this distance we call the event horizon, even light is trapped. That's why it looks black, because light can't be sent out from there. There's this video on black holes that I highly recommend. It's very fun. I'm not going to watch it now, but you can. It's linked. But we can figure out where this is. What is the radius of the event horizon, called the Schwarzschild radius? Basically, the escape velocity is the speed of light. And so the escape, right, is defined as kinetic energy plus potential energy equals 0 at a particular point. And we can plug in c, which is the speed of light. And we can solve for the radius. And so it's 2gm over c squared, the radius of the event horizon. What is that actual value? Well, it depends on the mass of the star. So if we have a black hole that has 10 sun masses, we can find this number, which is about 30 kilometers, which is pretty small, right? About 18 miles. Very, very small. And this is why black holes can be dangerous, because they have such a small radius. They're so compact that you can get really, really close to them without the shell theorems coming into effect. So we had this conceptual question. If the sun suddenly collapsed into a black hole, what would happen to the Earth? And that one is on your questionnaire, I believe. I mean, it doesn't say the sun, but the star. The Earth is orbiting the sun, and the truth is nothing would happen, because we wouldn't be close enough to be inside the Schwarzschild radius. Okay, something would happen, right? The sun would go out, and that would be difficult. But other than that, we would be unaffected. All right, that's it.